So I'd like to welcome everyone to the Oxford Set Theory Seminar, which is, I guess, currently the joint set theory seminar with Bristol and Oxford. And just for the record, we're recording this talk and we'll be putting it on the YouTube channel later on. So it's my pleasure to introduce today's speaker, Andreas Blass from the University of Michigan, and he is going to be speaking on the topic of ultrafilters on omega versus forcing, and he just assured me that he is going to set the ultrafilters fighting against forcing, and so I'm sure it will be an interesting battle that we'll see. So Andreas, why don't you go ahead and share your screen, and then we'll proceed.
Okay. Let's see.
For questions, please just kindly unmute yourself and go ahead and ask the question. That's what Andreas said, and we're going to go, I guess the talk will be up to 90 minutes, including any questions that arise. So we have 90 minutes.
Okay, thank you. So first of all, make sure everybody can hear me and can see the slide that's on the screen. If you can't, complain now. Okay, so I want, as I said in the abstract, I want to survey some results and some open questions. Many of the results are actually quite old ones. The open questions also, and about what happens when ultrafilters get tangled up with forcing. So the main topic is going to be the issue of preserving or destroying ultrafilters when you pass to a forcing extension. So first of all, I'm going to be talking only about non-principal ultrafilters on omega. That's not strictly true. Non-principal ultrafilters on countable sets, which I will biject to omega whenever it's convenient to do that. So I will say that a non-principal ultrafilter is preserved in a forcing extension. There's a temptation to say if it remains an ultrafilter, but that's not a good idea. Because the only time that happens is if you don't add reals. If you have any new subset of omega, then that will not be in the ultrafilter. Its complement will not be in the ultrafilter, and therefore what was an ultrafilter in the ground model will not be an ultrafilter in the extension. The right notion of preservation is that the ultrafilter in the ground model should generate an ultrafilter. In other words, if you take the ultrafilter of the ground model and then close it upward, close it under supersets in the extension, the result should be an ultrafilter. An equivalent way of saying that is that every new subset of omega either includes a set from the ground model ultrafilter, in which case it will be in the generated filter, or it's disjoint from a set in the ultrafilter, in which case its complement will be in the generated filter. So this is what you need in order to get an ultrafilter, in order to get you generating an ultrafilter in the extension. And if it's not, if the ultrafilter isn't preserved, then we'll say it's destroyed or killed by the forcing extension. Quite a few forcing extensions simply kill all the ultrafilters of the ground model in a couple of ways. The easiest example is probably Cohen forcing. It adjoins a subset of omega such that neither that subset nor its complement contains any infinite set from the ground model, let alone set from some specified ultrafilter. So the Cohen reel essentially splits all the infinite subsets of the ground model. For the same reason, if you join a random reel, you have killed all the ground model ultrafilters. For a slightly different reason, if you join a Matthias reel, it's not the case that the Matthias reel neither contains nor is disjoint from infinite sets in the ground model the way Cohen and random reels are. Matthias reel is disjoint from lots of infinite subsets of the ground model. But the key here is that a Matthias reel is a dominating reel. If you imagine a Matthias reel, okay, my hand waving goes like this. Omega looks like that. And a Matthias reel looks like there's a few here, and then it gets extremely widely spaced out. Technically, a Matthias reel encodes a dominating reel. And if you now look at the intervals between between consecutive elements of the Matthias reel, and take the union of every second of those intervals, it's easy to see that that union neither includes nor is disjoint from a set in the ground model. And furthermore, this has very little to do with being a Matthias reel. It has to do just with the fact that the Matthias reel is a dominating reel. So exactly the same argument applies, for instance, to Heckler reels and Lever reels. Anytime you add a dominating reel, a dominating member of omega to the omega, you have killed all the ground model ultrafilters. Okay, so there's a lot of nice examples that kill all ground model ultrafilters. Do all forcings do that? Maybe the whole topic disappears because ultrafilters are never preserved. Well, except of course, if you don't add reels, then they are trivially preserved. So in the future, even if I forget to say it, when I talk about ultrafilters, non-principal ultrafilters on omega, and when I talk about forcing extensions, I want forcing extensions that actually add reels. Well, so that's the question. Do the ultrafilters have any chance at all in this battle? Can they survive when a reel is added? And the answer is, yeah, sort of. The answer is at least consistently yes, by an old theorem of Baumgartner and Lever, which says that selective ultrafilters are preserved by Sachs forcing. So there is a way to add reels, Sachs forcing, and there may be some ultrafilters preserved. What about this? Maybe, well, it's not provable that selective ultrafilters exist. And I think this may be the right time to interpolate some definitions. Is that, yes, that's the next slide, good. An ultrafilter is selective if every function, remember this is an ultrafilter on omega, so we're looking at functions on the set where the ultrafilter lives. And the requirement for selectivity is that by restricting to a suitable set in that ultrafilter, the given function either becomes one-to-one or becomes constant on that subset. An equivalent way to say the same thing, instead of thinking of a function on omega, think of partitioning omega into the subsets on which f is constant. And this says if none of the pieces are in the ultrafilter, then a selector, a set with one element per piece, is in the ultrafilter. That's the basis of the terminology selective. Another name for the same thing is a Ramsey ultrafilter because of a theorem, I think due to Kunin back in the 60s, saying that selective ultrafilters actually have far stronger properties than the definition says. In particular, Ramsey's theorem holds with homogeneous sets in the ultrafilter. If you partition, say, the pairs from omega, or the 17 element subsets, any finite size will do, into two classes, there will be a set in the ultrafilter, all of whose subsets, pairs, 17 element, whatever, are in the same class. So that's selective ultrafilters, and a minor variation of that concept will also play a role later in the talk. So the definition is here. P-point ultrafilters, defined just like selective, except for one word. Instead of one-to-one, we have finite to one. Again, there are numerous equivalent definitions. I think I will have occasion to refer to at most one of them, namely that if you have countably many sets in the ultrafilter, then there is a single set in the ultrafilter that's almost included in all of them, included modulo a finite error. Such a set is called a pseudo intersection. So the selectives are the ones that showed up in the previous slide in the Baumgartner-Lever theorem, they are guaranteed to be preserved by Sachs forcing. It's been guaranteed for quite a long time. I'll get to p-points a little bit later. Let's see, what else needs to be said? What needs to be said is whether these things exist. And yeah, we don't really know. ZFC alone does not prove the existence of such ultrafilters. Kunin showed that there are no selectives when you add a lot of random reals, and Sherach had a somewhat more complicated construction of a model with no p-points. On the other hand, under various assumptions, including continuum hypothesis, there are lots of selective ultrafilters. Various assumptions here include Martin's axiom is good enough to get this result. So are some cardinal characteristic conditions like the covering number for bare category equal the continuum will do this. So if you're willing to go beyond ZFC, there are ways to get selective ultrafilters, but ZFC alone is not enough. And also, of course, any selective ultrafilter is a p-point, but assumptions like the continuum hypothesis will also give you non-selective p-points. And I might add, if you want ultrafilters that are not even p-points, ZFC does give you those. In fact, we'll see the construction of that before too long. Okay, let's see, what do I want to say about preservation? I guess I want to give a list of what kinds of ultrafilters are preserved by what kinds of forcing. So the first one here is just a repetition of what I already quoted from Baumgartner and Lever. And Baumgartner and Lever, I think in the same paper, showed that you can iterate that if you do a countable support iteration for omega-2 steps of Sachs forcing, then the selective ultrafilters of the ground model will generate selective ultrafilters in that extension. In particular, the extension, even though it doesn't satisfy the continuum hypothesis and doesn't satisfy any of the cardinal characteristic inequalities that I was just mumbling about, will still have selective ultrafilters anyway, because it has the selective ultrafilters from the ground model. Arnie Miller proved that p-points are preserved. So essentially just weakening the assumption of selectivity in the first item above. You only need a p-point and it will be preserved when a Sachs real is adjoined. P-points are also preserved when a Miller real is adjoined. Let's see, there are zillions of Millers in logic, but I believe every occurrence of Miller in this talk is Arnie Miller. And you can also do countable support omega step iterations of either the Sachs or the Miller forcing and preserve p-points. In fact, much more generally, if you do a countable support omega step iteration of a proper forcing where each step preserves p-points, then the iteration preserves p-points. This is a result of Sherach. If you quote papers, it's in a paper that Saharan and I wrote as a joint paper, but this result is definitely Saharan's. Okay, I said p-points would come up again. So here they are. First of all, there's sort of a dividing line between what kinds of forcings have what kinds of effects on ultrafilters. If you adjoin a real that is not majorized by any ground model real, the fancy name for that is that the forcing is not omega to the omega bounding, then the only ultrafilters that have a chance to be preserved are the p-points. I think that's in the same paper that I wrote with Saharan way back when. Preserved ultrafilters have to be p-points. Not only do they then generate an ultrafilter in the extension, but they continue to generate a p-point in the extension. One needs to be careful about that. If you have a selective ultrafilter in the ground model and you start doing Miller forcing, for example, the ultrafilter will generate an ultrafilter in the extension, but it won't generate a selective ultrafilter. It'll generate a P point that's not usually selective. So yes, one does need to be careful about that. So that's if the forcing is not omega to the omega bounding, it kills everything except P points. But it may preserve P points, as we saw on the previous slide. Miller forcing would be an example. An omega to the omega bounding proper forcing behaves quite differently. If it preserves some ultrafilters, U and a sequence of ultrafilters V sub n, then it preserves also what I call the sum of those V sub n's with respect to U. And I'm going to guess that that notation is not immediately known to everybody. So here's a definition of it. This is a definition that well, let's see. The only reason for reading this definition is to say something like, it's the set of X such that the set of A, such that the set of B, such that pair AB is in X, is in V sub A, is in U. And this is why the language of mathematics is only context-free and not regular, because by the time you get to the end, you're not really sure whether this parses correctly. I hope I've got the right number of braces in it. What's really going on is this. We're defining a collection of subsets, it'll be an ultrafilter, subsets of omega squared. So imagine omega by omega rectangle. And a set, imagine more. Imagine the ultrafilter U sitting on the base of that square, on that copy of omega. And imagine V sub n as sitting in the nth fiber. So there's a different, possibly different ultrafilter in every vertical column. And now what this says is that a subset of the square should count as large, meaning it's in this ultrafilter, if for almost all points on the horizontal axis, measured with respect to U, the intersection of that blob up here with that column is large in the sense that V sub n gives you for that column. And when you write that down, all the hand waving collapses to this one unreadable line. An important thing to notice about this is that no matter, as long as you're dealing with non-principal ultrafilters, as I always am in this talk, this sum is never a P point, essentially because the vertical projection from omega squared down to omega is not going to be constant on any set of the ultrafilter. That would put that set into a single column, whereas to be in the sum, it's got to be large in many columns as measured by U. Nor is the projection going to be finite to 1 on a set in U, on a set in this ultrafilter, because being finite to 1 means in those columns, it's only finite. It's not in V sub n. So I'm using the V sub n as non-principal here. So a sum of non-principal ultrafilters with respect to a non-principal U is never a P point, and yet it's not even particularly difficult to prove that any omega to the omega bounding forcing that preserves U and the V's will also preserve this. I said it's not difficult to prove. That's correct if I state it properly. I think I want an omega to the omega bounding. Oh, I did say it correctly. Proper forcing. Good. It's not particularly difficult to prove if you remember the correct statement that you're proving. With proper forcing, it does work quite nicely. So in particular, for example, Sachs forcing is omega to the omega bounding, proper, preserves all P points, So it preserves everything you can get as a p-point labeled sum of p-points. And then it preserves everything you can get as a p-point labeled sum of sums of, and so forth. And you can iterate, I guess, since you're allowed to take, you have countably many V's, you can actually keep the iteration going for omega-1 steps, and you get sort of iterated sums of p-points, and those are all preserved by Sachs forcing.
Andreas, I have a question. So can you explain what's wrong with the intuition that says if U and the V sub n's are all preserved by any forcing without any extra assumption, then okay, then every subset of the, you know, on the x-axis is I mean, that's generating an ultrafilter, and in each column the filter we're using on that column is generating an ultrafilter. And so why doesn't it just automatically preserve this sum?
Okay, if I try to do the obvious proof, where do I get in trouble? Okay, let me try and do the obvious proof. I remember getting in trouble with this once. That's why I was worried about saying things like proper. But okay, so what happens? Suppose U is preserved, suppose all the V sub n's are preserved, and now somebody gives me in the extension some subset of omega squared. Okay. In each column, the part of that subset in that column is either in or out of, either it's in Vn or its complement is in Vn. So I get a decision like that in each column. More precisely, I get a decision and the intersection of X with the column either includes a set from Vn or is disjoint from one from Vn. So in the extension, I have this sequence for each n. I have the answer, is it in Vn or not? And I have a good reason, namely a subset that's in the ground model Vn, right? The difficulty is that although I have that in each column, I don't necessarily have the sequence of those answers or of the witnessing sets in the V sub n's. And that gets me into at least one and possibly more kinds of trouble, because the next thing that I want to do is I want to say, let's let you make a decision about that. Okay, so you can make a decision. So there's a set in you such that all the, all those decisions are the same. And now what I'd like to say is, okay, shrink that to a ground model set in U because U is preserved. And now in the ground model, take that set in U and all the relevant witnesses from the VNs. And that I can't do in the ground model because the ground model doesn't see that sequence of witnesses. Okay. And essentially what is needed is, I'm not going to try and patch up the proof now, but the idea is that properness will let you, there's a countable collection of these witnesses that are each in the ground model, but the sequence of them isn't. Properness will give you a sequence in the ground model that includes those relevant ones. And then you want to use omega to the omega bounding to say that you really need to look at only finitely many things at a time rather than a whole omega sequence so that you can make intersections in the ground model, and that will give you the ground model set.
Okay, thank you very much.
Okay, good. So yeah, I do need hypotheses here because the result is false without the hypotheses. Okay, so Sachs forcing preserves some non-p-point ultrafilters. That's provided p-points exist. Because the way I got these non-p-point ultrafilters is by starting with some p-points, which are preserved thanks to Miller's result, and then forming sums of those which are not p-points. So in order to get preserved ultrafilters of any sort, everything that I've done so far has needed something beyond ZFC. Essentially, I needed enough stuff to get me some p-points. Okay, so there's a question, can I get more preservation? Question that occurred to me when I was preparing this talk, and I realized I don't know the answer, so I'll just mention the question. I think it's open, but it may just be a matter of my ignorance rather than genuine openness. Is it provable in ZFC that some ultrafilter is preserved. My guess is that it's not, that you actually need some non-trivial assumptions to get a preserved ultrafilter. Building a counter model, though, a model in which there's no preserved ultrafilter, is going to take some work, because at the very least, you have to make sure there are no p-points. And making sure there are no p-points is already, well, it's a result of Sherlock, which gives you a hint as to it's not entirely trivial. So there's a question. So I promised in the abstract to talk about some questions. So I've now kept the promise. I've talked about a question. I haven't said anything about answering it, but here's a question that I do know an answer to. Might it be the case that there's a forcing that preserves all the ultrafilters? The answer to this is no, and it's been known for quite some time. There's the answer. If a new reel gets added, then an ultrafilter gets destroyed. The history of this, I'm not too clear on, so I will instead tell you my history with this. My history with this is that I had heard this result. I'd seen it mentioned a few times, and yeah, that's a nice result, good. I don't remember whom it was attributed to. And at some point, not too long ago, well, long ago by some people's standards, but in the current century, at some point, that's not too long ago by my standards, I decided, you know, I really should learn what is going on there. What's the proof of this theorem? Unfortunately, the proof is easily available. It's in the Bartoshinsky-Yuda book, Set Theory on the Structure of the Real Line, which is sort of, I guess, the first place anybody would look for something like this. It's there. And even better, the proof is only about 1 page long. I think actually maybe a little bit less. Okay, so I decided, yeah, I'm going to read this proof. Yeah, I read the proof. And then I took out a sheet of paper and started making my own notes on how I would like to think about this. This is how I often do mathematics. You see what somebody else has done and then see how I would think about it if I were doing it. So I started writing things out, and I wrote it out in a way that I felt I could understand rather nicely. And then I looked at it and said, wait a minute, this proves more. The proof actually shows that there's an ultrafilter that's killed whenever you add new reels. In other words, in the theorem that I was looking up, in this one, the ultrafilter doesn't actually need to depend on the reel. There's an ultrafilter which will get killed no matter what reel you add, just as long as it's new. Okay, so there are these, I think I once called them fragile ultrafilters. They break whenever you do anything non-trivial. And it shows even more. There are, in a sense, lots of these ultrafilters. The notion of lots here is going to look kind of technical. There's an analytic filter on omega such that every ultrafilter extending it is killed whenever new reels are added. Now, again, people who are accustomed to working with analytic filters or their dual analytic ideals are going to recognize that this is a fairly strong statement about having lots of those ultrafilters, but let me explain why it's a fairly strong statement. First of all, analytic in this context means a filter is a subset of the power set of omega, which I think of as 2 to the omega, which I think of as the Cantor space. So topologize as a product of discrete copies of 2. And then analytic means what it means in descriptive set theory, projection of a Borel set. One of the nice things about analytic sets is that they all have the Baire property. They're also all the big measurable, and they do all kinds of other wonderful things. But for this one, I want is the bare property, because for filters, when a filter has the bare property, that gives you some additional information, which I don't think I put on the slide. No, so I'm just going to tell you. If a filter on omega is analytic, then it has a finite to one map to the sending it to the cofinite filter. So what does that mean? It means given this filter on omega, you can partition omega into intervals, so infinitely many finite intervals. I'm waving my hands like this, but I really should be doing something like the intervals get longer and longer rapidly. But you can partition omega into intervals such that every set in the filter meets all but finitely many of those intervals. That means in particular that such a filter is nowhere near an ultrafilter. I mean, if you're going to meet every one of these, all but finitely many of the intervals, then, for instance, nothing in the filter will be in or out of the union of the even-numbered intervals or any other infinite union. So there are lots of ways of splitting omega into two pieces where this filter never contains either piece. So filters with the bare property, in particular analytic filters, have lots and lots of ultrafilters extending them. And what this says is that for this particular F, all those lots and lots of ultrafilters are going to be killed whenever you add new reals. So fragility is very common. Okay. Yeah, I included a proof sketch here. Let's see, how am I doing for time? Oh, yeah, I can tell you some of the proof of this. So the proof is Bartoshinsky-Yuda's proof of this result, rewritten in a slightly different language, with the observation that it actually shows more than that. So here's how the proof sketch looks to me. I'm going to start by taking the Boolean algebra freely generated by a countably infinite set. This is a very familiar object because it's standard propositional logic, like first few weeks of a logic course. Think of G as the set of propositional variables, and B is all the formulas, everything you can get by applying Boolean operations to them up to logical equivalence. So I'm identifying equivalent formulas in order to make a Boolean algebra. Okay. I want to think of reals for this argument as being functions from G into 2. So if you like, identify G with omega, and now we're looking at reals in one of the usual senses. A function from propositional variables to 2, which I think of as true and false, canonically extends to a truth assignment on all propositional formulas. Just exactly, again, what you do when you talk about truth valuations in propositional logic. Or if you prefer, if you're an algebraist rather than a logician, what I'm saying here is that a function from the free generators into a Boolean algebra extends uniquely to a homomorphism from the freely generated Boolean algebra into that same target. In any case, main point of this sentence is just to introduce the notation with a bar over it for the canonical extension, and to make me worry that I probably forgot some bars later in the argument. I'm going to call a set X of formulas. I'll just say formulas, really meaning equivalence classes. Call a set of formulas small if there are infinitely many truth assignments that all give all the formulas in X the same truth value. There's something weird going on. Digression from the proof. There was something weird going on here. The proof in the Bartoshinsky-Yuda book has at the corresponding place that there should be not just an infinite set, but a perfect subset. So equivalently, an uncountable closed subset of this Cantor space. And the proof works fine with perfect. It works fine with infinite, as far as I can tell. And I've gone through it a couple of times, and it seems to continue to work each time. So there are several notions of small, all of which seem entirely adequate for this proof. So I'm taking the one that's probably simplest to state, infinite, but feel free to change it to perfect, especially if I get in trouble with this. But even if I don't get in trouble and you like perfect sets, go ahead with it. And I guess there are two main facts about this notion of smallness that are needed. The first one is that you can't cover the whole Boolean algebra B with finitely many of these small sets. If you give me finitely many of these small x's, there will be a formula that's not in any of them. I didn't write the proof down on the slide. That's why the slide says proof sketch at the top, but I think I'll wave my hands at the proof. Suppose somebody gives me finitely many of these x's, put them over here, subsets of the Boolean algebra. I'm going to wave my hands as though there are two, but there could just as well be any finite number. For each of those x's, I have over here an infinite collection, P, of truth assignments, each of which gives a constant value for everything in X. In particular, given any formula in this X, any two truth assignments from the corresponding P will have the same value for that formula. And likewise, given the formula in that X and two truth assignments in its version of P. Now, because each of these P's is an infinite set, I can easily choose from each of them two elements, which I'm going to call, say, the V and W from this one, and another V and W from that one, and if there are more of them, so that all the V's and all the W's are distinct. Okay, there's only finitely many of them, so it's easy. And each P is infinite, so that's easy to do. And now what I'm going to do is I'm going to say there is, well, let's see, how should I say this? Each of those V's and each of those W's that I picked, so if there were n of the x's, I picked 2n elements here. There are 2n distinct elements of this Cantor space. So there's a Clopin set that contains all n of the V's and none of the W's. I mean, you can separate any one from any other, and then you just take unions and intersections of those. Another way to say that, Clopin set in this space, that's given by a formula. It's the truth assignment satisfying some particular formula. So there's a formula over in the Boolean algebra that assigns to this V and W different truth values, because the formula is true for the V and false for the W. And it assigns to this V and W different truth values, and so forth. The fact that it assigns different values to V and W means it's not in that corresponding X. For the next X, different values for those V and W, not in the corresponding X. So I get a truth, I get a formula that's not in any of those finitely many X's. So that's all that's going on here. Another way to say it is the small sets generate a proper ideal of subsets of B. I need to be careful here. Well, actually, I and you need to be careful here, because people talk about ideals and filters and so on in Boolean algebras, and that's not what's going on here. This is an ideal of subsets of the Boolean algebra. So I'm thinking of the Boolean algebra as just a set and looking at ideals on that set as opposed to ideals in the Boolean algebra. And as I say, there's no real confusion here, except that putting that much reliance on the distinction between in and on is a little bit risky. So that's why I'm making this comment. Don't take that risk. This is going to be an ideal on B, not an ideal in B. Furthermore, more of the proof sketch, if I have a set in the ground model and a real not in the ground model, and the corresponding truth values for formulas are constant on this X, then X is necessarily small. And in fact, it's necessarily small even in the strong sense that there's a perfect set P in the ground model of truth assignments that give all of X constant truth values. This, I think, given time, maybe I better not get into too much detail about that. So let me just say this is essentially doing a Cantor-Bendixson analysis of what happens. Well, I can wave my hands a little bit. Look at the collection of truth assignments. Look in the ground model at truth assignments that are constant on X, or more precise, constant on each element of X. So there's a tree of approximations to those. A truth assignment is a function from omega, or G, into 2. Build a tree of finite approximations to those. Essentially, these are finite partial truth assignments that have not yet given any two elements of X different truth values. I want to show that that tree has a perfect subtree, because then the paths through that will be the perfect set P that I need. If it doesn't have a perfect subtree, you can do a Cantor-Bendixson analysis of it and show that since this, in the extension, R will be a path through the tree, and it's very hard for a new real to be a path through a non-perfect ground model tree, essentially by doing a Cantor-Bendixson analysis and showing that you could have produced R in the ground model. So I will just mumble Cantor-Bendixson at this point and not go into any more details. Once you have these results, this shows that if you have an ultrafilter disjoint from S, it's killed by all new reals, because take this new real, look at the extension R bar, function on B to 0 and 1. If an ultrafilter was going to be preserved, then it would have to contain a set on which that function, that two-valued function, is constant. But then that set would be small. So if the ultrafilter is disjoint from the ideal of small sets, then it's killed by all new reals. So this is enough to prove the first of my claims, that there are ultrafilters killed by all new reals. Furthermore, S is an analytic ideal. You go back to the definition of what it means to be a small set and count the quantifiers and see that it works. And again, it works even if you do the more complicated definition with a perfect set rather than an infinite set. And oh, actually, now I wrote out the argument that I gave you earlier. So I guess I can go through this quickly. It's an analytic ideal, hence meager. So the dual filter maps finite to 1 to the cofinite filter, and therefore is far from ultra. And that's the sense in which there are lots of ultrafilters that are killed by all new reals. So after I figured all this out, I found out that Arnie Miller had figured out a lot more. Well, not exactly the same things, but enough to essentially get all the same results. Miller actually has a characterization of when an ultrafilter is killed by adding some new reals. For any ultrafilter U, again, non-principal ultrafilter on omega, as always, the following are equivalent. Fragile. In other words, no matter what reel you add, it gets killed, like those ultrafilters that I was just talking about on the previous slides. No matter how you add a new reel, it gets killed. Equivalently, if you add a sax reel, it gets killed. That last line could be ambiguous. Killed whenever you add it, for every possible sax reel, or there exists a sax reel that kills it. Those are equivalent. If there exists a sax reel that kills it, then in fact every new reel kills it. This seems to be another instance of the general phenomenon that sax reels are the gentlest possible way to add new reels. If they kill you, then anything else will kill you even worse. Well, worse is not well defined, but if it were, that statement would be true. And here's a characterization that has nothing to do with just forcing. It's in the ground model. It says there's a perfect family of subsets of omega such that no single set decides uncountably many of them. And what do I mean by decides? It means it's included or disjoint. Another way to say this, there is no single set, sorry, better way to say it is, there's a perfect family such that whenever you take uncountably many of them, and look at which ones are in U and which ones are in the complement, replace those outside ones by their complement, so now they're all in U, and there should be no uncountable family of those whose intersection is in U, because that would be a set that decides them all. So the perfect family such that the intersection of any uncountably many of them that are in U is not in U, and the intersection of the complements of any uncountably many that are outside U is also not in U. So you can't get uncountably many of them collaborating on a single intersection. There's a lot that can be changed here without changing the definition. Uncountably many here, it would make no difference if instead of saying decide uncountably many, I said decide a whole perfect subset. The reason being that deciding whatever you want in particular is a closed condition. So if something decides uncountably many, it will decide a perfect subset because that closed set being uncountable will have a perfect subset. So uncountable can be made into perfect. I think, in fact, Arnie wrote this with perfect in his characterization, but for sneaky reasons of my own, I prefer to say uncountably many. Also, it doesn't really matter that you've got literally included and literally disjoint here. You can make it included mod finite and disjoint mod finite, in other words, put stars on the inclusion and the equality. It doesn't matter, because if you've got one set that does this in the weaker sense, so that you're allowing a finite error, but does it for uncountably many B's, then it has to do it with the same error for uncountably many B's, because there's only countably many finite sets that can be the error. And then by removing that finite set from your set in U, from A, you will get the decision in this stronger sense. So there's some flexibility in this third item. I just didn't want to give more and more easily equivalent characterizations. Okay. Let's see. I've still got a few minutes. So let me talk about something that looks completely different. And the final question that I'm going to want to raise is it completely different? So to talk about this, I need to say something about the so-called Tukey Order. Tukey Order is defined in considerable generality. I'll give the definition, but the only case I'm going to have to worry about is a very special case having to do with ultrafilters. So if you don't like general definitions, you can ignore this for a while until I hit ultrafilters. The general definition concerns upward directed partially ordered sets. So partial order in which every two elements have an upper bound, not necessarily least upper bound, just some kind of upper bound. Of course, it then follows that every finitely many elements have an upper bound, provided I remember to say that the set should be non-empty, so that the empty set has an upper bound. So for partially ordered sets like that, the Tukey order, so now P and Q are two such partially ordered sets. And the definition of P being above Q in Tukey order, by the way, many people will write this with a subscript T for Tukey. I'm omitting that partly because it's the only order on these partially ordered sets that I'm going to be looking at, and partly because greater than or equal to sub T looks too much like Turing reducibility to me, and might make things worse than they are. So here's the definition of the Tukey order. There's a function from P to Q, such that if you take a cofinal subset of P, its image is cofinal in Q. Cofinal means event that it gets above every element. So talking like a set theorist, it meets every cone. For every element in P, respectively Q, the cofinal set should have something above it. Okay, there are equivalent characterizations of this, which I won't bother with right now. That's the Tukey order. It is a pre-order, that is to say, it's reflexive, it's transitive, it's not anti-symmetric. Different partial orders can be Tukey equivalent. If you look at directed sets of some fixed cardinality, there is a highest one in the Tukey order, and it's above all the others, namely the collection of finite subsets of kappa ordered by inclusion. This is directed, right? Because we say if you have two finite subsets, there's another finite subset that includes both of them. Let's take the union. So that's very easily directed, and it is a straightforward exercise to see that indeed, if I take any other directed set of cardinality kappa, then there will be a function of this sort from this particular one to whatever other one you choose. Ultrafilters are coming back as quickly as possible. An ultrafilter is a directed set if you order it by reverse inclusion. Given any two sets in the ultrafilter, there's another one included in them both. I guess it's also directed by inclusion, but that's not very interesting because the whole set omega is the biggest element there. So ultrafilters are directed sets, and the interesting ordering is reverse inclusion. And yeah, an ultrafilter on omega has continuum many elements. That's fine. One says that U is Tukey top if it's at the top of the Tukey ordering, if it's the highest element, among directed sets of size continuum. And by the time you disentangle the definition of that, well, so first of all, since this is known to be the highest, the ultrafilter is Tukey top if it's Tukey equivalent to this one. Disentangle the definition of that via the Tukey ordering, and here's the equivalent version that I would like. There are continuum many sets in the ultrafilter such that the intersection of any infinitely many of them is not in U. Ultrafilters like that exist, which I hope I stated. No, I said it in equivalent form. Continuum many sets, such that no single set decides infinitely many of them. Such things exist. Attributing it to Isbell is a little iffy. Isbell was indeed, as far as I know, the first person to assert this. On the other hand, the example that's involved to build a Tukey Top Ultrafilter was built earlier, I think first by Pospisil, in proving that there are 2 to the continuum ultrafilters on omega. Because the construction here, well, let's see. Isbell's construction is this. Take a continuum-sized family of independent subsets of omega and build an ultrafilter that contains all those independent sets, but no intersection of infinitely many of them. One needs to check that that's possible, that the sets in the independent family and the intersections of, the complements of intersections of infinitely many of them have the finite intersection property, so you can extend to an ultrafilter. And then it's straightforward to check that this is a Tukey Top ultrafilter. So they exist. How about ultrafilters that are not Tukey Top? Well, here are a bunch of them. Any P point is known not to be Tukey Top. Any ultrafilter obtained from them by iterated summation. In fact, let's see, any ultrafilter, I was going to say something, but I'm not so sure it's true, so I won't say it. Any ultrafilter generated by fewer than continuum many sets. There are some others. There's something that I wrote a paper with Natasha Dobrinin and Dilip Raghavan on the next best thing to a P point. Those are also not Tukey Top. So there are lots of consistent examples, but we don't yet have any ZFC examples. So it might be consistent with ZFC, but all ultrafilters are Tukey Top. Again, getting a counter model to show that would involve, at the very least, making sure you have no P points. And again, you're doing Sherlock style work just to get the lack of P points, plus whatever else you need to handle this problem. My last slide, comparison between the last 2 slides and everything that went before. So here's everything that went before. Well, everything that went before was, can an ultrafilter survive? Is there a forcing that won't kill it? Well, if Sachs forcing kills it, everything kills it. So the equivalent question is, can I avoid being killed by Sachs forcing? And according to Miller's characterization, the being safe under Sachs forcing is the following property of an ultrafilter. Every perfect family of subsets of omega has uncountably many members decided by a single set in the ultrafilter. Not being Tukey Top has, from a slide or 2 back, this characterization. Every family of continuum many subsets of omega has infinitely many members decided by a single set. And you may notice that there's a certain similarity here, right? They're not the same, because this talks about perfect families, whereas this talks about any family of continuum many, not necessarily a well-behaved family. So this second version is talking about a lot more families that you have to worry about, but it requires less. It only says that you need to have infinitely many simultaneously decided things, whereas this one asks for uncountably many. So neither of these trivially implies the other. On the other hand, they're very similar. Might there be a common generalization, a common whatever, something that explains both? Well, p-points do both of these things. They're not killed by Sachs forcing, they're not Tukey top. I want to say, hey, look, there's a similarity. Maybe we can say something about p-points having some common generalization property. On the other hand, the proof that p-points do this and the proof that p-points do that look very different to me. I don't see a genuine similarity between the proofs, beyond the fact that they're both about p-points. Nevertheless, it's reasonable to ask, can we try for a common generalization? For example, here's a proposed common generalization. Take strengthening of both parts. So I'm looking at continuum, any continuum many, not necessarily perfect. So it could be some weird Bernstein set or whatever, okay? Yet I require for such sets having uncountably many rather than just infinitely many. So I'm taking sort of the first line from this description and the second line from this description, and the third line can come from either one because it's the same. Okay. So one might say, okay, maybe p-points will do this. Let me go to a place where I know there are lots of p-points, like continuum hypothesis. Assume the continuum hypothesis. Then do p-points satisfy this? No, they do not. In fact, the continuum hypothesis implies no ultrafilter does this. So this common generalization sort of overdid it, I guess. It's not clear what should be or could be happening here. So this is another of the questions that I had promised. What actually is the connection between being preserved by Sachs forcing and not being Tukey top? There are two properties that lots of ultrafilters have that consistently exist, but we don't know that any of them are guaranteed to exist. The characterizations look very similar, and when I try and merge the characterizations, it crashes. So, so I guess I will leave you with that question and stop there. Thank you.
Well, thank you very much, Andreas. That was really great. So why don't we open it up for questions now? Are there any questions? If you have a question, I think it's easiest to just unmute yourself and ask it. Philip, you're on mute still. We can't hear you.
I pressed it. Okay, can anyone hear me now?
Yes, I hear you.
So thanks, Andreas. Yes, that was very nice. About fragility, the fragile ultrafilters you were talking about a few slides back. So these are analytic. So if I were to ask you, could you have Borel fragile ultrafilters in the same sense, or is analytic the simplest possible?
So first of all, it's not the ultrafilters that are analytic. There's this analytic filter.
Sorry,
all
okay.
ultrafilter extensions do this.
Yes.
Can I get a Borel set? Let me see. Analytic filters do. Can I extend this filter to something Borel? There may be some nice soft general reason for that. Like analytic filters tend to have Borel extensions, but I don't think that's necessarily true. So unless there's a theorem that makes this trivial, I don't think it's true. Well, let me be careful. I don't think it can be obtained by the kind of proof that I was using. For all we know, remember, we don't yet have any, let's see, let me play it carefully. For all we know, it could be consistent with ZFC that all ultrafilters are fragile, in which case we could take the Borel filter of cofinite sets in that model and all its ultrafilter extensions there would be. So, so the question would need to be decorated with some things like, can it be proved in ZFC that there exists a Borel filter, all of whose ultrafilter extensions are fragile? And The answer to that is I don't know.
Right. But so there's nothing ruling it out that there could be a Borel filter who's
There is nothing
nothing known to rule it out.
Yeah, I don't immediately see any way to rule out even quite low level Borel filters doing this, because again, it would to show that something like that might very well be consistent with CFC for trivial reasons, like all ultrafilters are fragile. And in order to show that it's not provable in ZFC, you'd have to show consistency of at least some non-fragile ultrafilters, and we don't even know how to do that.
Yes. Right. Thank you. Thank you.
Sorry, I said that wrong. You'd have to get a model with appropriate non-fragile ultrafilters. We do have consistency of non-fragile ones because P points are not fragile. I might add here that we probably know somewhat more because the non-fragile things, so we've essentially said if an ultrafilter is fragile, it cannot extend the dual filter of the small sets. But more has to happen because if an ultrafilter, I'm getting this backwards, if an ultrafilter is fragile, let's see. An ultrafilter is non-fragile. The idea is the closure under summation is going to generate more. Oh, I take that back. No, skip that. Erase the last thing I said. Yeah, I should probably not try and say anything more about this without general policy. Think first, talk later. So I will see if I can think about it.
So I think George has a question from the chat.
Yes, regarding the question of Philip, if you restrict that problem to F sigma filters, that is like consistency false, right?
If you restrict the F sigma filters,
yes, there is no consistently. There is no F sigma filter that such that all its extensions are fragile.
I don't even know that. Again, let me fall back on, I should think before I talk, because yes, I mentioned to Philip that it might be that one could even get very low level Borel, and if sigma is indeed very low level Borel, but I don't immediately see why you couldn't improve the result even that far.
By extending to P points or something like that?
No, let's see, what can we do? No, I don't immediately see any approach to that. I have not seriously tried to lower this from analytic. I was looking at analytic essentially as just a way of saying there are lots of these ultrafilters because an analytic filter is what Adrian Matthias calls feeble, meaning finite to one projection to the cofinite filter. And I didn't really look into any improvements beyond analytic here. So again, I think I'll be much better off if I don't try and figure out something right now.
Thanks.
So Aaron has a question.
Thank you, and I hope it makes sense. Does this generalization of P points that you're maybe hoping for hold under Martin's axiom?
You mean this thing on the last slide?
Yeah.
Let's see. No, I think probably when I said CH implies that no ultrafilter does this. Let's see, every family C subsets of omega I have. Yeah, so there will be, let's see, if you have Martin's axiom but not CH, then you can build P points that are essentially generated by a tower of length continuum. And those will have this property because we have C subset. Let's see, yeah. So let's see. You can build, assume Martin's axiom, but not CH. You're going to build an ultrafilter by building an almost decreasing continuum length sequence of sets that is supposed to generate the ultrafilter. So the way you do that is at successive stages, you spend some time making sure that it's an ultrafilter by saying, okay, if I've got to a certain set at this stage, and I've got infinite, if I've got some subset of omega, at the next stage, I'll take a subset of this that's either in or out of the subset that I'm considering. And that way I'll make sure that at the end I've got an ultrafilter. You also spend some successor time making sure you get a P point. Actually, you probably don't even have to do that. Never mind. You'll be fine. Don't worry about it. At limit stages, just take a pseudo intersection of what you have before, because Martin's axiom tells you that the tower number equals continuum. There will be an infinite pseudo intersection, and you keep the construction going. So you get an ultrafilter generated by an almost decreasing continuum length sequence of subsets of omega. That will be a P point, because if you take any countably many of those sets, they won't be cofinal, because Martin's axiom, well, lots of things, continuum cofinal with omega. Martin's axiom says continuum is regular, so any countably many of these, there'll be a stage beyond those where you've got them inside them all. So you've got a P point, and now I claim if you give me continuum many subsets of that, there will be uncountably many of them that were in the ultrafilter by some stage of the construction. Essentially, because now I am using that the continuum is regular, in particular that it doesn't have cofinality omega 1. So that given any omega 1 sets that eventually get into the ultrafilter, there'll be a stage in my tower such that they're all supersets or almost supersets of that. And then again, by making a finite adjustment in that set, I can get those uncountably many decided by a single set. So yes, there will be ultrafilters that do this if you have, and there'll be P points if you have MA but not CH.
Interesting, thank you.
So I have a question, and that is, so have you ever given any thought to the sort of large cardinal analog of some of these questions? I mean, I would be interested, say, if kappa is a measurable cardinal, looking instead of at ultrafilters on omega, I want to look at kappa complete ultrafilters on kappa. And then you're asking, you know, whether those get killed whenever you add subsets to kappa and so on. It seems like many of the questions have direct analog in that realm. And do you know?
Certainly ask those questions, and I don't have any real answers there. Let's see.
I mean, the P point analog would be a normal ultrafilter.
It's not just a matter. Pardon?
The analog of P point would be something like normal ultrafilter, a normal measure on the measurable cardinal. And
well, actually, that's more analogous to selective. If you think about the characterizations of selectivity, and in particular Ramsey properties, normality gives you all of that.
Yes.
So I would think of normal ultrafilters and their isomorphic copies being the analog of selective. In fact, there's an actual theorem there that says that if you look at the Rudin-Kiesler ordering, the minimal things in the Rudin-Kiesler ordering of all ultrafilters on everything are the selective ultrafilters on omega and the normal ultrafilters and isomorphic copies thereof on measurable cardinals. So yes, there are analogs of those notions. One needs to be careful, of course, about, you don't want to just say add new subsets of kappa because, you know, you add a Pricri sequence to kappa and your ultrafilter has now become a cofinite filter on omega or something. So yeah, I guess the relevant things to ask are, what happens if you add subsets to kappa carefully so that you're not totally wrecking the whole thing? is there a good analog of the perfect set ideas? What's the analog of Sachs forcing at a measurable cardinal, for example? Maybe there is one, I don't know. Put another way, I don't know of one, but maybe somebody does.
Well, there's this generalized prickly forcing with these trees and so on. Maybe that's something.
Yeah,
long prickly forcing. I mean, where you're adding a kappa sequence instead of an omega sequence.
yeah. So there may be lots of things there, but no, I've only looked at omega. I haven't even looked at omega 1, let alone measurable cardinal.
If I can jump in on that, I know people have looked at kappa Sachs forcing where you have a club of splitting points. Things like Sly Friedman and Katie Thompson had results about measurability with that kind of forcing. So there has been some work on this, but not so much.
Okay, I mean, I guess the key thing for Sachs forcing is not so much the technical stuff, but the intuition that one gets after a while that Sachs forcing just barely adds a real and doesn't do anything more than what's needed to just add a real. And what one would like is if a forcing like the one you're describing does that for a measurable cardinal, that it just adds a new subset of kappa, but doesn't do anything more than is required in order to do that.
I think that there are some theorems using that forcing that control the number of measures in the extension, and so that would conform with the view that you're talking about, because not very many.
Nothing much new is happening. Yeah, so yeah, it's entirely possible that something analogous to that would happen. Yeah, so on that, I'm just going to have to say it looks interesting. I would want to know, for instance, how do fusion arguments work in that context? I assume that's a big ingredient of whatever is known about it. And yeah.
So are there other questions then? No? Okay, well then let's all thank Andreas for the wonderful talk. And next meeting of the Oxford Bristol Set Theory Seminar will be November 4th with Mirna Jamonia, and she's going to be speaking on wide Ehrenstein trees. So I hope to see you all there. This recording will be posted on the Oxford Set Theory Seminar YouTube channel probably in the next few days. I'll try to get it up. So thank you very much, and see you all on November 4th.
Okay, thank you.
Thank you.
Thanks,
Thank you.
Andreas. Thanks, Joel.
Thank you.
Thank you.
Thank you, Andreas. And nice to see you.
Thank you.
Thank you.
Sharing. Oh, thanks. Okay. I will.
Okay, so I'm going to close the meeting then.